Okay, good evening, everybody, and welcome to another session of organic chemistry. In today's session, we are going to conclude our discussion on chapter 15. Chapter 15 is concerned with the chemistry of benzene and benzene derivatives. If you recall, when we left on Thursday, we were discussing aromaticity and resonance, and so we are going to continue from there. But before we do that, a couple of announcements. I have posted the last year's first exam in Blackboard. So if you want to take a look at what the exam looks like, you should go to Blackboard. That is already posted. And also want to remind you that the first class exam is scheduled for next week, Thursday. That is November 6th. And I'm sorry. That is February 6th. Sorry about that. The next class exam is scheduled for next week, Thursday. That is February 6th. And because of that, we are going to have an online review session on Monday. So I want you to mark your calendar. So that will be Monday. We are going to have an online review session. I believe Monday is that February the 3rd, right? Okay, February 3rd at 8 p.m. Okay, so mark your calendar. I will send you the link to that session during the week, and I will also remind you on Thursday. Okay, so let us get the session started. I know you guys want us to go over the quiz questions. Indeed, those questions, the questions that I gave you in the quiz today, actually came from last year's exam. Okay. Okay, Asinda, can you go ahead and read this for us?
Yes. I-12 has been tried, is aromatic, whereas isodienone is non-aromatic. Explain what that is, resonance.
Okay, thank you. So what we want to do here is to test your knowledge of aromaticity. In other words, can you recall those conditions that make a molecule aromatic? Okay, conditions that make a molecule and those conditions collectively we refer to them as aromaticity. Okay, in other words, do you recall those conditions that make a molecule aromatic? Now, what they want you to do here is, of course, to use resonance in order to establish that this molecule here, this is aromatic, and this here is not aromatic. Okay, so let us go ahead and label these molecules. Let us call this molecule A, just for convenience, and this molecule B. Okay, taking a look at molecule A, let us draw the resonance structure for that. Oh, by the way, which will be the correct answer here? I mean, why is molecule A aromatic? Anybody has an idea? Anybody? You know, remember I gave you a list of 5 items, yes. Okay, well, but this also has sp2 in there. Molecule B also has sp2 carbons within the ring system, yes. 4n, exactly, correct. In other words, molecule A observes the Oculus rule. Okay, so that is what we are going to go into when we draw the resonance structure. Yes, Kiara?
I understand the form has 2 parts, but it takes what is the age of resonance structure?
Yes. Okay, so we are going to draw the resonance structure, then we'll explain it from there. Okay, so let us draw the resonance structure for molecule A. Keep in mind that this oxygen does have 2 pairs of non-bonding electrons. Okay, so you have a double bond here, and another double bond here, and then another one here. Okay. Now, if we draw the resonance structure for this molecule A, we could move this pi electron between oxygen and carbon to oxygen, because of course you know that oxygen is more electronegative than carbon. And you know this is the symbol for resonance. So now let us draw the resonance structure. So now we have 3 pairs of non-bonded electrons on oxygen. That means this carbon here will be positively charged. And then you see I have this pi electron here, and here. Okay? Now if you look at this resonance structure here for A, take a look at it. Look at this carbon here. This is an sp2 carbon. Keep in mind, from here, you know that this is an sp2 carbon. It's also an sp2 carbon right here. Now, it just so happens that the p orbital here does not have any electron. That is why it is positively charged. Okay? Now, so this molecule does meet all of the requirements for aromaticity. It's a cyclic molecule. All of the carbon atoms in the ring system are sp2, and then the molecule is flat. Okay? All the sp2 carbons. Because of the sp2 carbon, the molecule is flat. And we could also delocalize this electron here along the carbon chain of the molecule. In other words, I could write this, draw another resonance structure here, in which I move these 2 here. And I have this. Now the double bond will now be here. Now the positive charge will now be here. And here, this is a double bond here. In other words, I could delocalize this pi electron along the carbon chain of the ring system. You could do another resonance structure, moving these 2 here. The positive charge will be here. So the point is, this molecule does meet all of those requirements that make a molecule aromatic. Now the last requirement is the Oculus rule. In this case, 4n plus 2, because you have 6 pi electrons here, equals to 6. And if you work that out, n equals to 1. And Oculus rule says that as long as n equals to 0, 1, 2, 3, any integer, N goes to be 0, 1, 2, 3, or any integer, then that molecule will be aromatic, provided it meets all of the other requirements. Yes. This one, which one here? Because don't forget that we move this away. You don't count this here. This is not part of the ring system. Got to look at this ring system right here. Okay, and that's when we move the electron away from due to resonance. See, we're only looking at this right here. Okay. So therefore, molecule A is aromatic because it meets all of those requirements, and more importantly, it does obey the Ockhams rule. Okay. Okay, on the other hand, let us take a look at molecule B. You find that molecule B does not obey Ockhams rule. Even though it meets a lot of the requirements. Okay, let us take a look at this here. Okay, we move this pi electron to oxygen, just as we did here. What do we have? We have this. And this is positively charged. Okay, you notice here, all of these atoms within the ring system are all sp2 hybridized, but that doesn't make that molecule aromatic. As long as one of the conditions is not satisfied, then the molecule will not be aromatic. In this case, if you look at this, 4n plus 2 equals to 4 pi electrons. We only have 4 electrons. That means n equals to 0.5. N cannot be a fraction. That is what Ockhams rule is saying. N must be 0 or any integer. Is that clear? Okay, so in this case, the reason why the molecule A is aromatic is because it obeys Ockhams rules. It also obeys all of the other requirements for aromaticity. Okay, particularly when you draw the resonance structure. Here we could also draw resonance structure for this. So move this to here. Even though we can do all of that, it does not meet the requirement of the Ockhams rule. Therefore, it is not aromatic. Okay, so this is not aromatic. Okay, let us go to the next one. Okay, let's see here. Okay, Kiara Williams, I know we have two Kiara. Yes. Can you read this for us?
Provide the product for the following Diels-Alder reaction, indicating appropriate material chemistry.
Okay, thank you. Okay, so this question here is simply testing your knowledge of Diels-Alder reaction. Do you know what Diels-Alder reaction means? Okay, and also do you know the conditions for which you can do a Diels-Alder reaction? If you look at this molecule here, this is the diene, and this is your dienophile. If you look at the diene, you will find that it is in the cis conformation. I'm sorry, trans conformation. Now, what do we need to do in order to perform a Diels-Alder reaction on this molecule? You got to rotate the single bond between the carbon-carbon double bond so that you get the cis conformance. Okay. So in this case, you need to rotate. You need to rotate this bond so you get the cis conformer. It's almost as though this is what you have here. If you want to take a look at this model in my hand, so this is what you have, right? You see the double bond, and this is the single bond between them, right? Okay, in this case, this double bond is going up, this double bond is coming down, so we say they are trans to each other, relative to the single bond. So what do we need to do now? Simply hold this, you rotate the single bond, okay, and now you get the cis conformation. And you also notice something here. Look at the methyl group. This methyl group on this carbon here, and this methyl group on this carbon, they are pointing in the same direction. But when you rotate this here, they will now be oriented in different directions. Okay? This is going here, but this is coming here. So you could assume that they will be trans to each other in the product. Okay? Okay, so let us do the rotation here. Okay, so we say that this molecule, which is in the trans conformation, will be in equilibrium with the cis conformer. So we have this. Let me go ahead and number this here to make it easy for us. Let us call this carbon 1, 2, 3, 4, 5, and 6. Okay? And then we say this is 7 right here, and this is 8. Okay, so what do we have here? So this will be here. Let's complete this. So our carbon 1, 2, 3, 4, 5, and we'll say this is our 6, and therefore and this is our 7, and this is our 8. Okay? And on carbon 8, we now have a methyl on carbon 8 also, pointing in the other direction, which is here. Okay? So now we have this molecule dying in the cis conformation. Now what we want to do now is now have the dienophile pointed in such a way that we could see the attachment of the atoms. Okay, so we have the dienophile here. You can also see here we could use a dienophile that is a carbon-carbon triple bond. I'll just do this. Okay, continue our numbering. So I will say this is carbon 9 and this is 10. Okay, so what carbon will be attached to what carbon? 1 and 10. Okay, very good. So we are going to attach 1 and 10. Keep in mind Diels-Alder gives to a 6-member ring. And which other carbon? 8 and 9, very good. And so that is your 6-member ring right there, right? And then the new carbon-carbon bond will be where? Between 6 and 7, right? Okay, so once we do that, then we have Okay, so let us name this number, this carbon here. 1, 2, 3, 4, 5, and 6. So now we now have a 6-member ring. Okay. And this will be our 7, and this will be our 8 right here. And then of course this is our 9, and this will be our 10. Okay. So now let us look at all of the attachments. We have attached to carbon 10 the ester group right here. And also attached to carbon 9, we have another ester group. And now because we are starting with a carbon-carbon triple bond, we are actually going to have a carbon-carbon double bond here. So we only use one of those. Okay, now, also between carbon 6 and 7, we have a double bond. Okay, now, what about the stereochemistry? Take this out of here. The stereochemistry of the methyl group in position 1 and 8. What will be the stereochemistry, the relationship between them? Trans. Very good. Okay, I think we got everything. Okay? You follow that? Yes. Why the double bond between 6 and 7? Well, in the Diels-Alder reaction, don't forget, whenever you do a Diels-Alder reaction, if you look at your basic Diels-Alder reaction right here, right? Okay? The double bond will be in a position, the new double bond will be in a position where the single bond was before. Okay, and that is what this is. So remember, the single bond was here. And that's why we now have the double bond in position 6 and 7. Okay, so if you do this, you get this here. The new double bond will be here. If you number this, 1, 2, 3, 4, 5, and 6. And that is 1, 2, 3, 4, 5, and 6. You notice the new double bond is now between 2 and 3. That was where the single bond was before, yes. Yeah, go ahead. Say that again. The triple bond? Okay. Okay, what happened to the triple bond? Okay, don't forget one of the pi bond in the triple bond we have to use. If you look at this here, we are using this double bond here. So we have to use one of the pi electrons here to form the new bond with in the Diels-Alder reaction. And because we were starting with a triple bond, and that is why we still have a double bond left. Okay, so let us go to the next one. Okay, Frederick. Yes. Can you read? Oof. Let me take this off. I didn't want to do that. Okay. Yeah, I was practicing before I came to class. Okay, so let's take this off and then we do this together. Okay, Freddie, go ahead.
Reaction of 2 methyl ethylene with Alkenes HCl produces 3 chloro 2 methyl 1 butane and 4 chloro 2 methyl 2 butane. Provide the reaction mechanism that accounts for this
Okay, thank you. Okay, so in this reaction here, of course, we are testing your knowledge of electrophilic addition reactions. To a conjugated system. Okay, and in this case, the conjugated system is 2-methyl 1,3-butadiene reacting with hydrogen chloride. Okay, so let us go ahead and draw that here. That is a 2-methyl 1,3-butadiene, and then we have to react this with hydrogen chloride. And they told us, upon reaction with hydrogen chloride, you get 2 products. And these products, 3-chloro-3-methyl-1-butene and 4-chloro-2-methyl-2-butene. Okay, so let us draw those products. Of course, this question is also testing your knowledge of nomenclature. So they told us we got this product here. Now we also obtain this product. Okay, so taking a look at this product, the 2 products, let us call this A and let us call this B. Taking a look at A, what kind of product is A? Is that a 1,2 addition product or 1,4 addition product? 1,2 addition product, very good. So this is a 1,2 addition product. And of course, about B, 1,4 addition product. Okay. In other words, in 1,4 addition product, let us go ahead and number this here. This carbon 1, 2, 3, and 4. Okay. Okay. In 1,2 addition products, hydrogen attacks itself to carbon 1, and of course the chlorine comes in as a nucleophile to carbon 2, which is right here, and that's what you get here. And of course the 1,4, the hydrogen goes to carbon 1, and then the chlorine as a nucleophile goes to carbon number 4. Okay, so now what we need to do is provide the reaction mechanism. Okay, let us do the mechanism for the 1,2 addition. What is going to happen first? Any idea? Yes. Okay, you say that? Oh, okay. Okay, the pi electron here, you say the pi electron will attack the proton of the HCl? Okay. Just a minute. Notice I draw my arrow. You draw your arrow from where you have the electron, which is acting as a nucleophile, to where you have the electrophile, which is the positive charge or positively charged species. Okay, yeah, go ahead. Okay. See that? Okay. Okay, so now that's the first thing that happens, and then we get this here, this intermediate carbocation. Let's show the hydrogen attached to there, and we have this here. Now this is positively charged. Now we have this. Okay. Plus you have your chloride here. Okay, so now what happens next? Before my initial carbon, the chloride, very good. So now the chloride will now act as a nucleophile, attach the carbocation, and then you get this here. That's how you got this. Yes.
Okay. The part A where it's like 3-chloro, 3-methyl, you started numbering from the right.
Let me see. Let me know.
How
This molecule here.
yeah, for number 8, letter 8, like on the right side. You see how the first product is supposed to be 3-chloro, 3-methyl, so you started number 1, you see, starting from the right side.
Oh, okay. I see. You said this is 3-chloro, right?
Yeah.
Okay. 3-methyl, 1-butene. Okay. You are talking about the nomenclature. Is that what? Okay. And so the question is, why is this?
Something you have to start numbering from the right order to satisfy.
Okay. Don't forget this is an alkene. So you have to start in a position to give the carbon-carbon double bond the lowest possible number.
No.
Okay. So this is named as an alkene. Okay? Okay, now, so we get this. So that is how, this is the mechanism for the, how we obtain the 1,2 addition product. Now let us do the same thing for the 1,3 addition product. So what I want to do now, let us take this intermediate carbocation. Okay? I'm going to write it here. The same carbocation, I will write it right here. So that's the first thing that you form, right? Now, what is going to happen to this carbocation now in order for us to form this product? What is going to happen? Resonance? Exactly. Okay. We move the pi electron between 3 and 4. And then you have a resonance structure. Okay, now you form this primary allylic carbocation. Now what happens next? The chloride comes in, exactly. So now the chloride comes in again, acting as a nucleophile to attack this, and that is how you got this product here. Good? Is that clear? Now, supposing that I want to make this a little bit more complicated in an exam, right? Supposing I did this. Everybody got this? Well, let me go to a new page. Supposing I did this. And I say hydrogen bromide. Keep in mind, we could also use hydrogen bromide instead of hydrogen chloride. Hydrogen bromide reacts with this molecule here, right? Let us number this carbon here. Let's say carbon 1, 2, 3, 4, 5, 6, 7, and 8. Supposing I say this is the product that we obtain. Okay, let us see here. This is 1. If you wanted to use a red pen. 1, 2, 3, 4, 5, 6, 7, and 8. Now I said we got, instead of this, we got this product. Let us call it product B. And I say, give me the mechanism for this reaction. You should be able to do that, right? It's the same thing that we just did. It's the same concept, right? What is going on here? Oh, okay. You draw the, you give the initial carbocation, right? Hydrogen goes here. You form a carbocation on carbon number 2. And before the bromide gets a chance to attack that carbon, you get resonance. All of these pi electrons will move. Because all of these are all conjugated. Those pi electrons, those double bonds are conjugated with each other. And therefore, eventually you have a positive charge on carbon number 8. And then the bromide will simply come in and attack that. You follow that? So if I do that in an exam, they'll say, well, you didn't give this to us in class. It's the same concept, yes. Yes, this would be a 1-8 addition. This would be a 1-8 addition. It would be a 1-8 addition. Okay? Okay, very good. Let's go to the last one. Okay, let me see what I've not called. Yeah. Where's so Bethlehem was here? She disappeared. Okay, Robin, as you Robin trying to cover your eyes. Robin, go and read this for us. Go ahead. Yeah, I said read this for us. Okay. Kiara Wallace, can you read this for us?
Oh, you told me Robert?
No.
Oh, provide the product of the following Diels-Alder reaction.
Okay, thank you. They provide the product of the following Diels-Alder reaction. Okay. Okay, so another Diels-Alder reaction, you guys should be able to do this, right? Okay, now if you look at this here, what kind of conformation is this molecule? Let's call this molecule A. Trans, right. So what do we need to do? Rotate it to give the, exactly. So what we need to do here, we need to rotate this bond right here, okay? So that we are going to get the cis conformer. So we say this would be that right here. Okay, let me number this. Okay, we say this is 1, 2, 3. Oh no, this is 3. This is 4, and we call this 5. Okay, so that is 1, 2, 3, 4, and 5. And now we want to place the dienophile next to it. We are starting with a trans dienophile, so that is this one here. And then of course this is going in the other direction. Okay, so let us call this carbon number 6 and carbon number 7. So where are the attachments? 1 and 7? Okay, very good. So we are going to attach 1 and 7, and then 4 and 6. Very good. Okay. And then the new carbon-carbon double bond will be between Between 2 and 3. Very good. Okay, so we get this. So go ahead and write the 6-member ring. Okay. We'll say that if that is the case, we'll say this is carbon 1. Say this is carbon 1, carbon 2, carbon 3, 4. Okay, that means that 5 will be here. That is 5, and then we say this will be 6, and this is 7. Okay, so now on carbon number 6 we have the ester group. And on carbon number 7, another ester group. What will be the stereochemistry? Trans. Very good. And the double bond, the new double bond will be where? 2 and 3. Very good. Okay. Everybody follow that. Okay, so Diels-Alder reaction is very simple. As long as you know what carbon to attach to which carbon, then you should not get anything. You should not get it wrong. Okay. So at this point, let us start go to today's discussion on chapter 15. Okay, if you recall, when we left on on Thursday, we were discussing aromaticity. We gave you those conditions, these 5 conditions here that will make a molecule aromatic. Okay. Now, what I want to do now is simply give you a few examples of aromatic molecules. Most of these will be molecules that are benzene derivatives. Keep in mind, this is benzene. We also told you that benzene is a resonance hybrid of 2 resonance structures, these 2 here. Okay, so let us give you more examples of aromatic molecules. Okay, of course you know benzene. Okay, here this is a molecule we call toluene. Now keep in mind, when we say a molecule is aromatic, we are simply referring to the cyclic part of the molecule. Okay, the cyclic part of the molecule. Doesn't mean that this whole molecule is aromatic. Simply means that this part of the molecule here is aromatic. Okay. The same thing here. This molecule we call benzaldehyde. Part of the molecule is aromatic. Okay. Okay. A couple more examples of aromatic molecules. This happens to be ions. If you take a look at this, this is similar to the one I gave you in class, the quiz that I just gave you. Take a look at this molecule here. Call this A and we call this B. Okay. Take a look at molecule A. We see here this cyclic. All of the carbon within the cyclic ring system, they are all sp2 hybridides. All of these are sp2 hybridides. The same thing on this carbon here, sp2 hybridides. Now we also have this pair of non-bonding electron here is in a p orbital. Okay, so it is in a p orbital. And that p orbital will be in resonance with the rest of the other p orbital in the pi system. So keep in mind there is a p orbital here, one here. They are overlapping, and those electrons could simply delocalize within the ring system. So therefore, we say this molecule is aromatic. Of course, you know here it does have 6, what we consider to be 6 pi electrons. So it does obey the Ockhams rule. The same thing here. Take a look at this molecule here. It's a cyclic molecule. Each one of these atoms in the ring system is sp2 hybridized. And this is also sp2 hybridized. The only feature here is that this carbon here is positively charged. In other words, the p orbital on this carbon is vacant. So therefore, this pi electron could move into those p orbitals. You could have electron delocalization all along the ring system. Okay? So therefore, we consider this molecule also aromatic. And of course, you will see here, it does obey the Ockhams rule. Okay? It also obeys Ockhams rule. Now, we don't want to leave you to thinking that the only aromatic compounds must have carbon atoms within the ring system. There are some aromatic molecules that have other atoms within the ring system. For example, take a look at these molecules here. You have pyridine, a tauphine, a paro. Okay, let me use this here as an example. Actually, this non-bonding pair of electrons should be here. I want to rewrite it so that take a look at this here. Nitrogen is here, and hydrogen is attached to nitrogen. Then you have this double bond here, another double bond here, forming a pi electron system. And then you have this, a non-bonding pair of electrons on nitrogen. So what do we have here? This non-bonding pair of electrons on nitrogen is it must be in a p orbital. It is in a p orbital. Okay? And this nitrogen is also sp2 hybridized. It's an sp2 atom. This carbon is sp2. The same thing here. So all of the atoms within the ring system, they are all sp2 atoms. So this does make the requirement for aromaticity. Okay? Of course, if you take a look at the number of pi electrons that we have in this ring system, 6. So obeys Ockhams rule. Okay. Now let us take a look at this here. Some of you will wonder how come we have 2 pairs of non-bonding electrons on sulfur. Okay. Now this is what happens. Only one pair of these 2 pairs is in a p orbital. The other one here, you could think of it as in an sp2. Let me use a different color pen. Think of this as in an sp2 orbital, and this one here in a p orbital, which would be, okay? Okay, so of these 2 pairs of non-bonding electrons, only 2 of them, only one pair is involved in the electron delocalization within the ring system, okay? So therefore, these 2 electrons will be delocalized within this ring system here. So in essence, we only have 6 pi electrons in this molecule, and that is why this molecule is aromatic, okay? Because it also obeys the Ockhams rule. Okay, now I want to now go to nomenclature of aromatic compounds. I think we've seen enough examples of aromatic molecules. Yes. Okay. Okay, before we leave, let us now discuss nomenclature of aromatic compounds.
But how purity is aromatic?
Very good. Okay. Why is pyridine aromatic? Okay. Very good question. What happens here? Remember I told you about this here. What happens here? This here, it is not in a p orbital. Okay, think of it, because this nitrogen is an sp2 atom. sp2 atom. This is an sp2 hybridized orbital right here. Those two electrons are in an sp2 hybridized orbital. You know, the sp2 hybridized orbital will be here. For you to have overlap delocalization, the p orbital is here, p orbital is here, and that is why they overlap side by side. But whenever you have a pair of electrons in an hybrid orbital, it's on the same plane, okay, as this other atom there, so they cannot overlap. Okay, so in essence, therefore, this pair of electrons here, this is in an sp2 hybridized orbital. Okay, so therefore, it does not, it is not involved in the aromatic ring system right here. Yes.
So technically, the first picture you circled is those two non-bonding electrons doesn't either, but the two in the ring does.
Yes.
Right. Okay.
Yeah. What? Okay. This is what happens. Okay. I know. Okay. Let me explain.
What you're saying, when you circle
Yeah.
two non-bonding electrons here, those
Those are not part of the ring system. Yes, because those are in the sp2 hybridized orbitals. Okay. The only one that will be in the ring system will be, keep in mind, this double bond here, one electron is coming from nitrogen, the other electron is coming from carbon. Both of those are in the p orbital and they overlap, and that's why you get this here. Okay, but this one is not involved in the electron delocalization. Okay, so anyway, yes. Which one? Why is it?
Yeah.
Okay. Yeah, another good question. Now, keep in mind these molecules, what they want to do, they want to assume a very stable condition. So for this molecule to be stable, the best hybridization for sulfur would be sp2 hybridized. So molecules decide, okay, I want to, for us to be stable, this molecule, this atom must be sp2, this atom must be sp2. So we cannot force that. Okay, so this is what happens in nature. Just simply decide, okay, aromaticity is very good. In order for us to have aromaticity, sulfur will assume an sp2 hybridized condition. Okay. Okay. Anyway, so let us go to nomenclature. These are just examples of other aromatic molecules. By the way, this is aspirin. You see, aromatic molecules are very important pharmaceutical material. And of course, this is Tylenol, for those of you who use Tylenol. Okay, many developing countries and in Europe, they call this paracetamol. Okay, you can see here the aromatic ring system is there, so it is very important structural feature of organic molecules, particularly those that we use in pharmaceutical drugs. Okay, now let us start the discussion on nomenclature. All these molecules on this slide, you need to know them. These are the basis for most of the nomenclature of the aromatic molecules that we are going to be discussing. You need to commit all of this to memory. In other words, this here we call toluene. It could be a base name. This here phenol, hydroxy attached to benzene. This amino group attached to benzene, we call this aniline. So all of this you need to know. The aldehyde group attached to benzene, we call that benzaldehyde. Of course, the carboxyl group attached to benzene, we call it benzoic acid. Of course, you know benzene. Okay, this is a carbon-carbon double bond attached to benzene, we call it styrene. Each one of these will be a base name for the nomenclature of most aromatic compounds. Okay, most of the aromatic compounds we are going to be discussing will be those that are mostly derived from benzene. Okay. Now, given that information, of course, you could see here, you just call it bromobenzene. You simply just attach the prefix to the name benzene. This is bromine here. It's a bromobenzene. Okay, this is nitrobenzene. You see here. Now, this group is called N-propo. Okay, so that simply becomes N-propobenzene. Now, supposing we have multiple substituents on the benzene ring. Supposing we have multiple substituents on the benzene ring. In that case, we follow all of the rules of nomenclature that we have been using before. You assign numbers, positional numbers to all of the substituents so that you have the lowest possible combination of numbers. You assign positional numbers to all of the substituents so that you obtain the lowest combination of numbers. Okay, for example, if you take a look at this here, we want to call this benzene, the benzene derivative. Of course, we number this here, carbon 1, 2, 3, and 4. Okay, we have to do that in order to give the lowest combination of numbers to those substituents. Okay, now when you do that, now to give the complete name, notice what we've done here. Now you have to follow the alphabetizing order. So this becomes 4-bromo, 1,2-dimethylbenzene. You have to follow alphabetizing order to give the complete name for each one of these. Okay. Here, we are naming this as a phenol. Remember I gave you on the last table that those compounds could be used as base name. The phenol is this here. Okay, that is the phenolic molecule. And then once we do that, what that means is the carbon attached to the hydroxy group will be carbon number 1, and then you assign positional numbers to all of the substituents so that you are going to give them the lowest combination of numbers. Okay. Okay, so this now becomes 2,5-dimethylphenol, methyl in the 2 position of phenol, and methyl in the 5 position of phenol. Okay, about this one here. We have 2,4,6. Now we are using base name toluene. In other words, we are using this as the base name. Okay, which means that the carbon that the methyl group is attached to will be carbon number 1. And then once you do that, the other substituent will be assigned positional numbers so that you give them the lowest possible combination of numbers. Okay? So these molecules become 2,4,6-trinitrotoluene. Now, yes.
Do you have to give it the base name toluene, or you could decide to just choose the methyl as a normal methyl and name it?
Yes, benzene. Yeah, you could do that. Generally, the rule of thumb is if use as fewer substituents as possible. Okay. In this case, you will be using a lot of substituents if you want to call it benzene. So it's just better to simply just call it toluene. That way you reduce the number of substituents. Yeah, but if you do that, that's okay. Yes. This here? This one? Okay. Okay, keep in mind, we want to name this a phenol. Okay, if you want to name it a phenol, that means the carbon that the hydroxy group is attached to must be carbon number 1. Okay? Okay? Okay, now, there is some, yes.
When it comes to phenol, it doesn't put double bonds in the ring, doesn't matter at all anymore.
When you say
Isn't the double bond rule before the...
Oh, no, this is not a double bond. This is benzene. This molecule here, this is the phenol. This is your base name right here. Okay?
But I'm saying when it comes to numbering, how come we didn't go the opposite way, counterclockwise?
If we did that, then this would be 1, this would be 2, this would be 3, right?
Right.
Okay, but then the combination of numbers will be greater. You are going to have 3, okay, 4, 5, 6. So you're going to have 3 and 6.
Yeah, I see, but I thought the double bond rule came from...
No, there is no double bond here. This is a benzene. This is benzene. This is not an alkene. This is benzene. Okay. Okay. Anyway, there is another alternative name that we have. Whenever you have only 2 substituents, say for example, you have this. If I have this, okay, if I have that, and then I now want to introduce another substituent. Now this methyl group on benzene, of course, is attached to this carbon here. Okay, so therefore, this position here, the 2 position relative to that methyl group, we will call this an auto position. Okay, sometimes we abbreviate as O. And then the 3 position relative to this methyl group, keep in mind this will be 1 right here. We will refer to this as meta position. Okay, sometimes we just abbreviate as M. And the 4 position, this is 2, this is 3. The 4 position here, we refer to this as para position. And very often we abbreviate as P. And so to name this, therefore, take a look at this here. What we have here, we say methyl dimethyl benzene. In other words, they are a 1-3 relationship to each other. Or if you may want to call it M or M dimethyl benzene. You could abbreviate the meta to M. About this one here. The base name here is what? What is the base name? Benzaldehyde. So if the base name is benzaldehyde, this chlorine is in the para position, okay, which will be the 4 position. So we call that para-chlorobenzaldehyde or p-chlorobenzaldehyde. Okay. Okay. The same thing here. This other example here. There are 2 chlorine atoms next to each other, 1, 2 to each other, and they will be auto to each other. So you say auto dichlorobenzene or O dichlorobenzene. Okay. And I think we have finished chapter 15. Oh, okay, we've got 2 more minutes. Okay. 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 The last thing I want to tell you about to lead to the chapter 16 is you got this? Okay.
No.
Yes. Okay. Just one more point, and then we'll finish chapter 15. Okay. Remember, coming back to Akira, your point about double bond. Okay. If you have this, if I have this, right, and I do this right here, no, let me use bromine. Let me use and I do this. What do you think the product will be? Dibromo, right? Okay. The bromine will add to this double bond, right? Okay, very good. Okay. If I do this, I do the same thing. Okay, you are going to get bromine attaching itself to those double bonds. On the other hand, if I now take here and now listen very carefully now.
Yeah, that doesn't work.
If I now take this, right? If I take this by itself, no reaction. Because benzene does not react as if it contains carbon-carbon double bond. So therefore, no reaction. So what we need to do here, what benzene does, instead of undergoing addition reaction, benzene does not undergo addition reaction under normal condition. Okay, let me say that. Okay. On the other hand, it undergoes what we call electrophilic aromatic substitution reaction. So when we come back, we'll tell you what that means, okay? In essence, if we have this here, for benzene to undergo that kind of reaction, you will need, in this case, bromine, okay, in the presence of a catalyst, and instead of undergoing addition reaction, it replaces the hydrogen. So this is an example of electrophilic aromatic substitution reaction. So what have we done here? We have substituted hydrogen for bromine. And those are the kind of reactions that we are going to be seeing in chapter 16. Okay, so folks, I will see you on Thursday.
Can you keep it up for